So today we're going to start going backwards. So first semester and part of this semester, we've been doing derivatives, right? So how do you take a derivative and go backwards? Okay. So I have three examples up here of three slightly different functions. Okay. But look at this. What would be here? The function is f of x is equal to x to the fifth plus 3. So the question is, what's the derivative of this? So what is f prime of x? Well, we'd have to apply the power rule here, right? So this would be 5x to the fourth plus, and then the derivative of 3 is just 0. So the derivative is 5x to the fourth, okay? So for this one, f of x equals x to the fifth minus 4. So the derivative of this one, f prime of x, would be 5x to the fourth minus 4. So minus 4, derivative of 4 would just be 0. So we wouldn't have to write it. For this one, f prime of x is equal to 5x to the fourth plus the derivative of 7, which is 0. Okay, so I want us to take a look and see, all right, what's the difference? Because the derivative came out every single time the exact same. Okay, so how can we go backwards, right? And so we never know, if you look at this, right, because these were all constants, when I took the derivative of it, we wound up with 0, right? So when we have a derivative, we don't know if that came from a function that has a constant, right? Like plus 3 here, or minus 4, or plus 7. We don't know, all right? Okay, so what we know is that this could have come from a function that has a constant. So we're going to be putting a plus c on this, okay, which stands for a constant, all right? Now, how do I go from here to here? So take a look what happened. Okay, we're multiplying by 5, and we have a power of 4. And if we have this, how would we go backwards? Well, we got to get the power to become a 5, right? Now, why did it become a 4? Because we subtracted 1. So how do we go backwards? We add 1, okay? And how do we get rid of this 5? Because this 5 came down. Well, we're going to have to divide by it, okay? So we're going to have to add 1 to the power and divide by the new power. So if you look at this, given f prime of x is equal to 7x to the 6th, what could f of x have come from? Well, okay, we're going to add 1 to the power, right? So that means f of x could have been 7x to the 7th, right? Because to get this derivative, this had to go down by 1, right? And how do I get rid of this 7, right? So if I did that, I'm multiplying by 7. How do I go backwards and do multiplying by 7? I need to divide by 7 and then add a constant, because I don't know this derivative, this constant would have been 0, and I won't see it here, okay? So these 7s cancel, and that means f of x is equal to x to the 7th plus some constant c. All right. You can always check by taking the derivative. What happens if I take the derivative of x to the 7th? It becomes 7x to the 6th. That's what we get, right? And then if this is a constant, when we go to take the derivative of it, we wouldn't see it in the derivative. Okay. All right. So there's all new notation for this to mean antiderivative. Okay. And so the new notation, there's actually a couple ways we write this. All right, but it's called integral notation, and it comes from the letter S, but it's been morphed into this. All right, so it's just a little curl here and come down and curl back up. And we say 7x to the 6th. And I should have said this f prime of x, you could also write this, because it's f prime of x, you could have written it as dy over dx is equal to 7x to the 6th. This could have been written that way too. And so what we're going to be, this is going to make more sense in a little bit, okay, in the next few days. But what we have right here is dx. So this dx actually comes up and we multiply it, all right? So this 7x to the 6th, this little part right here, that's called the integrand. That's what we're integrating. Integrand. And this dx is the variable that it's the variable of integration. It's kind of like the dy over, well, it comes from this. It has to do with like dy and dx and all of that. And this will make more sense as we get more and more into antiderivatives, okay? But this is called the variable of integration. Remember when we did derivatives and we said, it's the derivative with respect to this, and I just jumped in and started doing that. That's kind of the same way with this, okay? This variable of integration, all right? All right, now we're gonna quickly kind of go over some basic formulas, and they directly come from knowing the derivatives, okay? So I'm gonna go over some formulas next with you guys. So we know the derivative of a constant is 0, which means the integral of 0 dx would have to come from a constant c, all right? The derivative of a number times x is just the number. So like the derivative of 2x is just 2. Okay, so that means if we take the integral of a constant dx, that's going to come from constant k times x. So k times x plus a constant c. And we don't know what the c is. There's going to be a way to figure out later on, but right now we don't know. All right. If we have, this is the opposite of the power rule. If we have x to the n dx, all right, now that's power has been dropped down by 1, right? So the integral of this, or antiderivative, would be x to the n plus 1 power. We would need to add, and that's what we did up here, added 1 to the power, and then divide by that new power, n plus 1, and then again, plus some constant c. Because if we take the derivative of this n plus 1 is going to come down. So we're multiplying by n plus 1, but we're also dividing. So those are going to cancel, and we'd subtract 1, which would be left us with the n. Okay. The integral of e to the x dx. So what can we take the derivative of that would give us this e to the x? Well, it's e to the x. So this is just e to the x plus some constant c. All right. Some other ones that we should know. The integral. Well, I know if I take the derivative of sine x, that would be cosine x. So that would mean the antiderivative of cosine x, or the integral of cosine x, would equal sine x. So the integral of cosine x dx is equal to sine of x plus c. Why? Because if I take the derivative of sine x, I get cosine x. And if I take the derivative of a constant, I get 0. Okay, now this is going to be, well, let's do some others that were kind of straightforward, okay? Let's do secant squared x dx. So what could I take the derivative of that would give me secant squared x? And it would be tan x. So this is equal to tan of x plus some constant c. Because if I take the derivative of tan x, it gives me secant squared x. What is the integral of secant x? Tangent of x dx. And so what could I take the derivative of that would give me secant x times tan x, and the derivative of secant x? So that means when we anti-differentiate, right, take the antiderivative or the integral, that's going to equal secant x plus some constant c. Okay? All right. So now what if I have the integral of cosecant squared x dx? Well, I know if I take the derivative of cotangent x, I'm going to get negative cosecant squared x. That means this would have to have come from negative cotangent x plus some constant c. And I should have done sine x before this one, but too late. I already did it. All right, so the integral is sine of x dx. Okay, so I know if I take the derivative of cosine x, I get negative sine of x. So to go backwards, if I have sine of x, that must have come from negative cosine of x. So this is equal to negative cosine of x plus some constant c. Because if I take the derivative of cosine x, it gives me negative sine x, and I already have a negative, so a negative of a negative makes a positive, okay? All right, and then the next one is the integral of cosecant x, cotangent x dx. So I know if I take the derivative of cosecant x, I get negative cosecant x cotangent x. Well, that must mean that if you anti-differentiate, this would come out to be negative cosecant x plus some constant c. All right. And then we have a few more, okay? The next ones I want to do, they're going to be a little different. If we take, we can't use the power rule on this one, next one, okay? If we take the integral of 1 over x dx, okay? This right here and now, okay, 1 over x. So what could we take the derivative that would give us 1 over x? And you should be thinking ln of x. And you'd be absolutely right. However, 1 over x, this x can be any number. This could be negative, this could be positive. The only thing it couldn't be is 0, okay? All right, so this is going to equal ln of x. But it's not just ln of x, because this x, it could be any value, negative or positive. We have to put an absolute value on this. So the integral of 1 over x dx actually becomes the natural log of the absolute value of x plus some constant c. And so the absolute value takes care of this x being negative. That's the only way I can really kind of explain it to you right now, okay? There are going to be some other ways. And you may be thinking, well, couldn't I just rewrite it as x to the negative 1? And there's going to be a problem with that I'll show you in just a little bit, okay? So we did e to the x. We did 1 over x. Another one is that we should know is the integral of a to the x dx. So what is the integral of some number raised to the x power? Okay, and if you recall, this one, the derivative of a to the x is a to the x natural log of a. So this would have to have come from a to the x over ln of a plus some constant c. And so why? Because if you take the derivative of a to the x, you get a to the x ln of a, and so I need to divide by that to get the ln of a to cancel out, and you have this constant, and that would derivative that would be 0. Okay. And then we have the sum and difference rule, and then the constant. Okay. So if you have something like this, and we're going to use this today a lot. Okay. If you have a constant times f of x dx, just like derivatives, what we can do is bring the constant out. So k times, and then this just becomes the integral of f of x dx. So we can pull that constant always out from the integral, okay? And then the last thing we can do is this. If we have the integral of f of x, I'm going to put a bracket around this, f of x plus or minus g of x dx, we can break this up into the integral of f of x dx. So we can do them separately when we, just like derivatives, okay? We can take the derivative of each one individually, and this one would be plus or minus, and then the integral of g of x dx. So a sum or difference we can break up into individual integrals. That's going to allow me to like integrate a polynomial, okay? Because if I have like x to the 5th and a plus x to the 4th, that's going to allow me, because I can just do each one individually. All right. So there's going to be other rules, but these are all the rules that come from us knowing our derivatives really, really well. Okay. All right. Right now, probably the most important one for us is this. This is the power rule for integrals. Okay. We add 1 to the power and we divide by that new power. Okay. So we're adding 1 to the power and we're dividing by that same new power. All right, guys. And you can just think of, okay, you can think of like, all right, if I take the derivative of this, it gives me this. Oh, that means if I integrate this, it will give me whatever I took the derivative of, okay? You'll see in a minute what I'm talking about. All right, let's do some. Just like with derivatives, we're going to a lot of times need to rewrite the integral before we actually integrate, okay? So 1 over x squared, I would rewrite this one as the integral of, and instead of writing 1 over x squared, we can rewrite that as x to the negative 2 and then dx. And we can apply the power rule now to this, okay? So we're going to add 1 to this power, so that makes x. If we add 1 to the negative 2, that makes negative 1, and we're going to divide by that new power. So divide by negative 1 and then plus some constant c. Now, what does this mean? What does negative x and negative 1 mean? It means negative 1 over x plus c. So that would be the answer to this integral, okay? This one right here, we're going to need to add, all right? Or not add. We're going to have to rewrite this as a fraction. Sorry. So this is the integral of x to the 1/2 power dx. Now, because it's a power, I can use the power rule, all right? So this is going to be x to the, and I'm going to need to add 1 whole to this. So adding 1 whole to 1/2 would be adding 2 halves. So this becomes 3 halves. Okay, now I'm going to say you really don't want to write this because you're going to wind up with complex fractions. Whenever your new power is going to be a fraction, you have to divide by that new one, right? But if you divide by 3 halves, that is equivalent to multiplying by the reciprocal of it, all right, which is 2/3. So this is actually going to become 2/3 x to the 3 halves. Multiplying by 2/3 is the same as dividing by 3 halves, okay, plus some constant c. So this becomes, cleaning this up, this becomes 2x to the 3 halves over 3 plus c. Okay, so for this one, because this 2 is a constant, I'm going to pull it out and I can rewrite this one as 2 times the integral of sine of x dx. Okay, so I know if I take the derivative of cosine, right, I get negative sine. That means if I integrate sine, I would get negative cosine. So this becomes 2 times negative cosine of x plus some constant c, which multiplying these together, you get negative 2 cosine of x plus some constant c. All right, this next one is where, okay, this is 3 times 1 over x. So this 3 can be pulled out, and this becomes 3 times the integral of 1 over x and then dx. And the integral of 1 over x, all right, we should start to know that one. Okay, what could we take the derivative that would give us 1 over x? Well, it's ln, right? It's the natural log. Okay, so this is 3 times ln of, but it can't be just ln of x. It has to be ln of the absolute value of x plus c. That forces this x to be positive, right? If it's 0 here, we can't integrate it, all right? But if this was negative, like 1, you can have a value of 1 over like negative 3. But if it's 1 over negative 3, this becomes positive 3, and then you can take the natural log of it. So that's the whole idea behind the absolute, needing the absolute value here, okay? So really nothing to simplify here, okay? This would just be, I would just write this as 3 times the ln of absolute value of x plus c. Same thing as what I just wrote right there. Okay, so let me go over something that's a common mistake, all right? And that is to try and rewrite this trying to use the power rule, okay? Which is completely understandable. You just got to, if you're probably going to do this, just realize when you do this, like where the mistake lands, okay? So I want to show you, I'm going to flat out say this is wrong. So don't do it this way, and you're gonna see why it's wrong. And if you start to do that this way, I understand. I'm not gonna get upset with you because I mean I would probably do it that way, just learning this. But you got to realize, like, you got to catch your mistake, okay? Like what you're gonna get doesn't make sense, and here's why it doesn't make sense. You may have been thinking, well, Mr. Mitchell, couldn't I rewrite that as 3x to the negative 1, kind of like I did this one? And yeah, you could. All right, so this becomes, let's say 3x to the negative 1 dx. And I want you to take a look and see what happens if we follow along this line of logic, okay? This is a constant, so I could bring it out. So this would be 3 times the integral of x to the -1 dx, okay? And you go, okay, that's just a power rule for integrals. Okay, so if you try to apply the power rule, we're going to add 1 to this power. All right, so this becomes 3 times x to the 0. And now we need to divide by that new power of 0. And do you see what happened? We are dividing by 0, right? And we'd have plus c. And so now we're dividing by 0. So that's why this one problem, the power rule doesn't work. Okay, so if you ever rewrite an integral as x to the -1, realize you cannot use the power rule on that, because you're going to add 1 to the power, which causes it to be 0. And then you have to divide by that new power. And so you'll be dividing by 0. So that's why if you do this, I understand, just cross it out and go, whoa, 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 right? Put the brakes on, buddy. Okay, you can't do it that way, right? Okay, all right, so just put on the brakes when you see this and go, oh, wait, you can't do it that way. All right, so there's got to be another way that Mr. Mitchell showed me, right? And you go, oh, wait, ln of absolute value of x, although you probably won't remember the absolute value of x quite yet, okay? You'll see it enough that I think you'll start going, oh, when I integrate 1 over x, it's ln of absolute value of x, okay? All right, so this next one, what you have to realize is that this is a constant, okay? So this is really right here that's not being written is the integral of 1 dx. So what could you take the derivative that would give you 1? Well, you'd have to have an x being multiplied by it, right? So anytime you have the integral of dx or 1 dx, that's always just going to be x plus c. And that's it, okay? This next one is because we're adding, okay? We can actually, I'm gonna write this all out for the first time, and then from here on out, like the next one, we're just gonna do, okay? So this one, because I have a sum of 2 functions, I can rewrite this as the integral of x dx, adding the integral of 2 dx. Okay, so applying the power rule to this, I add 1 to the power, and that would make me a power of 2 and divide by that. So this becomes x squared over 2 plus, and this would have some constant c1. And you're going to see why I'm calling it c1 in just a second, okay? And then, so when I integrate this, I'm going to get a constant out of it because this is a function all by itself, okay? Then I'm going to add this integral, right? Well, this is a constant, okay? The only way you get a constant when you take the derivative is to have it be a power of x. So this becomes plus 2x plus some other constant, c sub 2. Well, if this is a constant and this is a constant, we can just write that as one constant because we would be able to add these together, okay? So really what this becomes is x squared over 2 plus 2x plus these 2 constants combined to make just one big constant, c. All right, so if you do these individually, you can just realize that you're going to have individual constants, right? And then you combine those all together and get a constant. Well, it's just like as if you integrated this each one individually, right? So that's what we're going to do the next one, okay? So we're not going to break it up. I don't expect you to break it up. We're just going to do, when you see a difference or sum, we're just going to do each one. Like this is 3x to the 4th minus, and then we're going to do 5x squared, and then plus, and then x. Okay, so we're going to add 1 to this power, which is going to become 5, and we're going to divide by that new power of 5. So this becomes 3x to the 5th over 5 minus, and this is 5, and we're going to add 1 to the power, which makes x cubed, and divide by the 3, and then plus, this is x to the 1st, so this is going to become plus x squared over 2, and then each of these had a constant, and we're just going to combine them all and one big constant at the end. All right, that's your answer to this. That's the integral. This is the integral of this. Okay, if you were to take the derivative of this, right? And another way you could write this is 3/5 x to the 5th minus 5/3 x cubed plus 1/2 x squared plus the constant c. This is helpful because if you were to take the derivative, right, you'd have to go 3/5 times 5x to the 4th. This 5 that you're multiplying we'll undo this 5 and you're left with 3x to the 4th. See how that works? And you could do each one individually like that. All right, guys, let's go to the next example. All right, so what we need to do on this one is we know how to integrate when it's x to a power, all right? And this square root of x, right, is x to the 1/2. So that's what I would start out doing, okay? That this is the same as the integral of x plus 1 over x to the 1/2 and then dx. So we're adding two things in the numerator, and then we have this denominator of 1/2, right? And so you could think of this, all right, as you did this in elementary school, this is adding two fractions with the common denominator of x to the 1/2, right? So we could rewrite this as the integral of x over x to the 1/2. I'm going to put parentheses around here, and then plus 1 over x to the 1/2, and then close parenthesis, and then dx. All right, this is one way of doing it. This isn't the only way to doing it, but this is one way of doing it, is you can look at this as being, oh, I can just break these up and divide each one of those by this x to the 1/2. Okay, so this is, so we could apply exponent rules. This one becomes x to the negative 1/2. This one is x to the 2/2, but now I have to subtract the 1/2. So this becomes x to the 1/2. Okay, so we have the integral of, and then we'd have x to the 1/2, because this would be 2/2 minus the 1/2, which gives you the 1/2, and then plus, and then x to the negative 1/2, because I can rewrite this. I want x to a power, right? So this one, the way I'm going to write x to the power is write it as x to the negative 1/2 power, and then dx. And now we're going to add to this. Now the exponents are fractions. So instead of dividing, we're going to be multiplying by the reciprocal. Okay. So if I add 1 to this, that'd be adding 2/2. So that makes x to the 3/2 power. Divide by 3/2, but the same as dividing by 3/2 is to multiply by 2/3. And so I'm going to multiply by 2/3. All right. And then I'm going to add 1 to this, right? So that makes adding 2/2 to this makes x to the 1/2. So I'm going to add, and then x to the 1/2. You want to leave a little bit of space here to write the multiplication, okay? So I'm adding 1 to this, so that's adding 2/2 to this, and that's my new power is going to be 1/2. I don't want to divide by 1/2. Instead, I want to multiply by the reciprocal of that, which would be 2/1, and then plus some constant c. So now it's just a matter of cleaning this up. So this becomes 2/3 x to the 3/2 power plus, and 2/1, we would just write 2, x to the 1/2, and then plus some constant c. Okay, and that's the power rule. So this is where, okay, you have to rewrite it. Now, another way of looking at this problem is you could, all right, instead of doing it the way I did it here, you could also do, and I just want to give you options, okay? So I want to show you this. I'm not going to work it all the way out. You could rewrite this as x plus 1 times x to the, and this becomes x to the negative 1/2 dx. And then if you went back and distributed that, you would get this right here. Okay, and so we'd be back to this way right here. Okay, just another way of looking at it. Okay, so it could be this or this. You know, either one of these would work. I should do it like this. Okay, so you could come this way and do it here to here, or you could go from here and then to here. Okay. You do need to show your work though, so I understand and I look at it and go, okay, you know what you're doing. Okay. All right, let's do another problem. And for this next problem, okay, it's really helpful if you understand the trig identities. This is gonna require a trig identity. Okay, so you know how to, you need to rewrite this. You don't have anything on that first page where we wrote all the rules, anything that looks like this. So could you rewrite this? And there is a way to do it, okay? And the way to look at this problem, and this is just gonna come from experience, the more you do this, the more, and the more mistakes you do, you learn from those mistakes and you realize, oh, that's not the right way of doing it, okay? Cosine squared x means cosine x times cosine x. So I'm actually gonna break this up into 1 over cosine of x, and I'm going to multiply that by sine of x over cosine of x, and then dx. Now, you may be thinking, Ms. Mitchell, why did you think of doing it that way? All right, so I saw sine x, and I see a cosine x down here, and I know if I have sine x over cosine x over cosine x is tangent x. So this becomes a tangent x, and then I also look at this, wait a minute, that's secant x, right? 1 over cosine x is secant x. So that's where I'm going with this. So 1 over cosine x becomes secant of x, and sine x over cosine x becomes tangent of x, and then dx. And okay, so what is it that I could take the derivative of and get secant x times tan x? And what you could take the derivative of is secant x. So that would mean the antiderivative of secant x tan x, this is a derivative, right? It came from taking the derivative of secant x. So the answer to this is secant x plus some constant c. And this relied on you looking at and realizing, oh, sine x over cosine x is tan x. Okay, so I would, it's not a for sure thing. You not necessarily like every time you see sine x over cosine x, switch it to tan x, but a lot of times that is one option. Okay, all right, guys. All right, that's it. That's the last example for today. All right. Hopefully you're finding this a little bit easier. You are going to have problems if you don't have your derivative rules memorized, because, and you've been, you just need to have those memorized, right? So that you can recognize, oh, that's the derivative of this, right? And then you can go, oh, that the answer to this integral or antiderivative is this function, okay? All right, you guys, that's it. See you later.